So related to the Rolle's theorem is this mean value theorem. It's a lot like it, some slight variations. Okay. So let f be a function that satisfies two hypotheses. Rolle's had three. Mean value theorem has two. Number one, f is continuous on AB, and two, f is differentiable on AB. Open, not including it. Then there's a value c, a number c, in AB, such that f prime of c equals f of b minus f of a over b minus a. Okay, so a couple of notes on that. Very much like Rolle's theorem, right? Except it's got two hypotheses. Matter of fact, hypothesis 1 and hypothesis 2 are very same as Rolle's theorem, except I don't have hypothesis 3. So I don't have that f of a equals f of b hypothesis. I just have those first two. Then there's a number c in AB, that's the same as Rolle's, such that f prime of c, and so here's the other difference in Rolle's theorem, from Rolle's theorem, is that instead of having it equal 0, it equals this. And we'll talk about what that means here in just a second. But very similar, but it's actually, I guess more, we can apply it to more things because we don't have that third hypothesis there. But anyway, yeah, now this conclusion, there is an equivalent, I think in this statement of these homework problems I've given you, they kind of sometimes list this conclusion differently. You could say, instead of f prime of c equals that, you could say f prime of c times b minus a equals f of b minus f of a. For whatever reason that you choose to do that. It's the same thing though, they just have multiplied b minus a over, if you will, right? Multiply both sides by b minus a. Okay. All right. So let's think about what this means graphically speaking. Here's what this means. So Rolle's theorem said you got the two function values, continuous, differential between them, then you got a horizontal tangent. Well, what this mean value theorem says is if I've got a to b, and in this case the two function values don't have to be equal, so let's just say they're not. We'll go up higher for f of b, it could be lower, still works. But as long as you've got continuous differentiable on a to b, so no breaks, no corners, a to b, here's what the conclusion is. So I just kind of drew a generic type line there. Could do anything as long as it doesn't have a corner or a break in it. The conclusion here is I've got the derivative of c, a c value where the derivative at c equals this. Now, do you recognize this at all? What is that? Isn't that the slope formula? So this right here is the slope of the points, slope of the line between the points at B and A. So this right here is the slope of this line right here. isn't it? That would be the slope of that line. So what this theorem says is there's a c value that has the derivative at c equal to that slope. And so if you go along here, the slopes of points along the way here, at some point, yeah, we're going to hit maybe, I'm going to say right along in there, that has the same slope as that. And so this theorem guarantees that there is that c value in A to B where that slope matches the slope between those 2 points. That's what the theorem says. Okay? All right, so let's put in another graph here. Call this high point here 2. And then we'll put 5 kind of over here. So I'm going to go 2 to 5. All right, so let's estimate. So this is y equals f of x. Estimate the values of c that satisfy the conclusion of the mean value theorem in BT for the interval 2 to 5. Estimate the values of c that satisfy the conclusion of the mean value theorem. So yours, since I've drawn this up here kind of free-handed, yours may be slightly bit different, but let's put in 3 and 4 here to give you some guidance. All right. Well, just like we did on my previous graph here, what I want to do is just kind of think about, I can draw it in. The conclusion says I need a c value that matches this slope. Well, what's the slope on this one? The slope on this one is I've got this line that goes through those 2 endpoints, 2 to 5. I want to find a c value, and if there's more than one, we'll use it. But in this particular case, I want to find a tangent slope that matches that. So you just kind of think your way around. All right, so if I drew in a tangent here, you know, that's not going to be it. If I drew one around here, obviously no. I've got to get along on this side, don't I? It's got to be somewhere over in here. Looks like a little before 4 is a 0, so it's somewhere on the other side there. I'm going to call it, I'm going to say right there. Like I said, it's just kind of an estimate. Here's maybe right at 4. Mine's looks like a little bit my scale there. Just on the other side of 4. So that would be my c value. C would be whatever that is. That's my c value, about 4.1. Is what I'm going to say. And I don't think there's any others that would match it, because if I keep going around, the slopes aren't matching. So, okay, we good? All right. Here's another one. So there's only 2 hypotheses on that one that you would have to check. So, like we did with Rolle's theorem, let's verify the hypotheses of the mean value theorem. And then find the values of C that satisfy conclusion of mean value theorem. A little wordy. But same idea as we were doing with Rolle's theorem. Verify the hypotheses, because like I said, you've got to have both of them for mean value theorem to work before you can go to the conclusion. Draw your conclusion there. Have a valid conclusion. Okay, so number one, we'll do a couple of these. Number one, the f of x is going to be x squared plus 4x plus 5. And then the interval is 3 to 7. Verify the hypothesis. And so again, verifying the hypothesis it's just kind of stating, so hypothesis 1 is f is continuous on AB, so is f continuous on 3, 7 here? Well again, it's a parabola. There's nowhere that's not continuous. Yes, that is true. F, if I wanted to kind of state it, F is continuous, just so they would know, I know what I'm talking about there. F is continuous for all real numbers. If you want to, negative infinity, positive infinity. So it's definitely continuous 3 to 7. Same thing for hypothesis 2, right? Hypothesis 2, F is differentiable on 3. We're asking ourselves, F is differentiable on 3, 7? Yeah, because that function is differentiable for all real numbers. Or some equivalence. See there, okay. All right, so that's verifying the hypothesis. And so then the values of C, or value, sometimes there may be more than one. So how do we do the values of C here? Well, on Rolle's theorem, we just got the derivative and set it equal to 0. We've got a little more, another step, if you will. Because remember the conclusion is we've got f prime of C, since I erased it, I'll write it again. I've got f prime of C is f of B minus f of A over B minus A. So when you go into mean value, you don't know what value you want the derivative equal to. That's what you have to establish first. And so what you want to do first is compute this f of B, the slope, if you will. With me there? So in this case, since that's A, that's B, f of B, so I do f of 7 minus f of 3 over 7 minus 3. Yes? That's the value that I would have there. So f of 7, let's see, f of 7 be 49 plus 28 plus 5. 33, is that 82? 82, is that right? F of 3 would be 9 plus 12 plus 5. That's 26. Believe that? 82? What I'm worried about is 82. I believe that's 82. And then that's divided by 4, so I've got 82 minus 26, 56 divided by 4. Oh, let's go for 14. I get 14. So the value of this is 14. Well, so the C that satisfies the conclusion then is I've got f prime of C equals that. So in this case, I don't set the derivative equals 0. I want the derivative equals 14. Now what's my derivative? 2x plus 4. So I get 2x plus 4 equals 14. With me there? We're used to setting derivative equals 0, but here we set derivative equal to 14 to satisfy the conclusion. And see what we get. So we got minus 4, 2x equals 10 divided by 2, you got x is 5. Now, for that to be the C value, what does it have to be? It has to be in the range there, 3 to 7. It is, so that's our C value. So the C is going to be 5 because it's in 3 to 7. So 5 would satisfy that, which, again, noticing there, it's right smack dab in the middle, but that won't always happen. You can't just always jump to the middle. It won't always be the middle. All right? Let me try another one here. This has got a couple of different pieces. All right. So number 2. All right, f of x equals x minus 1 over x minus 5. And I'm going there 1 to 4. So same setup. Verify the hypothesis of mean value theorem and find the values of C that satisfy the conclusion. All right, so hypothesis 1 is f is continuous on AB, so 1, 4. Is that true? Well, previously we said, well, f is continuous everywhere. That's not the case here. F is not continuous at 5, is it? But why does that not affect the mean value theorem hypothesis? It's not in the interval, right? If I picked 1 to 6, I'd be in trouble. But I picked 1 to 4. So f is not continuous at x equals 5, but it's continuous everywhere else. So it is continuous on 1 to 4, okay? So that's okay. Even though there is somewhere it's not continuous in the for the domain we're talking about. Okay? Hypothesis 2, f is differentiable on AB, which is 1, 4, without the influence. Is that true? Well, yeah, it's, again, at discontinuities, it's not going to be differentiable. So it's not differentiable at 5, again. But is there anywhere else that's not differentiable? Well, we could go ahead, let's go ahead and get the derivative here for this one. So we've got the derivative be x minus 5, quotient rule, times 1, derivative of the high, minus x minus 1 times the derivative of the low, which is 1, over low squared. Which that's going to be x minus 5 minus x plus 1 divided by x minus 5 squared, which is just going to be negative 4 over x minus 5 to the 4, minus 5 squared. That's going to be my derivative. And so looking at that derivative, yeah, again, the only place that's not going to be, I'm not going to have a derivative is at 5. There isn't a derivative at 5. So is that, yes. Is f differentiable on 1 to 4? Yes. It is only not differentiable at x equals 5. Something like that. So if I had included 5 here, that'd be a problem. But 5 is not included, so. All right? So, what are my values of C? Well, again, I want f prime of c equal f of b. So let's start with this slope. What is f of b? Minus f of a over b minus a and b. Well, again, we've got our a and b. A is 1, b is 4, so it'll be f of 4 minus f of 1 over 4 minus 1. So f of 4 would be 3 over negative 1, negative 3. F of 1 would be 0 over negative 5. That's 0. That's nice. And then 4 minus 1, so it's negative 3/4. Negative 0.75. Oh, I'm sorry. It's not even that. It's just negative 1. 4 minus 1 is 3, so it's negative 3 over 3. It's just negative 1. Even better. So yeah, now I want f prime of c equals that, and so what am I going to solve? Well, now I solve the derivative, which is that. So I want so I want the derivative, negative 4 over x minus 5 squared. That'd be my derivative. Equals f, well, that's equal to negative 1. So it's just this equation here. A little more complicated equation. Multiply both sides by x minus 5 squared. One way to go. Clear that out. So you got negative 4 equals, so it'd be negative 1 times, square that out, you get x squared minus 10x plus 25. And so you got negative 4 equals negative x squared plus 10x minus 25. Yeah, we got an x squared equation. I'm going to go ahead and bring, since x squared is negative, I'm going to go ahead and bring these terms over. I'd be thinking easier to go the other way, but so let's add the x squared minus the 10x and add the 25 to both sides. Get rid of it there, and so that's going to be x squared minus 10x plus 21 equals 0. Easier for me to factor, so do it that way. Don't have to do it that way, but that does factor. It's x minus 7 and x minus 3. And so we've got x minus 7 equals 0, so you got x is 7. X minus 3 equals 0, so you got x is 3. Two possibilities. However, we just need one of them, or just one of them is our c value. There could be two c values, possibly. But in this case, there's only one. Why? We're talking about the interval 1 to 4, aren't we? 7's outside the interval, so it's our c value is 3. There could be two, but they both have to be in the interval. So in this case, c is 3 is the one that we want. Yes? This is okay. Okay. I got one more. Here it's, again, another problem where we don't get to talk a lot about theorems in this course, but another question here relating to how theorems work. All right, so for f of x equals the absolute value of x minus 1, is there a c, a number c in 0, 3, such that f prime of c equals f of 3 minus f of 0 over 3 minus 0. So obviously might notice there that that's the conclusion of the mean value theorem. This is a good one for a couple of reasons. All right, so is there a C in 0 to 3 such that f prime of C? All right, so what do we have here? What is the f of 3 minus f of 0? What is that? I mean, may not have to get that, but let's go ahead and think. Is there yeah, I do have to get what number is that? What's f of 3? Plug in 3. 3 minus 1, absolute value, so that's 2. F of 3 is 2. F of 0, absolute value 0 minus 1, that's absolute value negative 1, which is positive 1. So the top's 2 minus 1, the bottom's 3 minus 0, 3. It's 1/3, right? So this is 1/3. So is there a derivative? Is there a C value so the derivative equals 1/3? Well, again, a couple of reasons for doing this. Let's review here what's going to be the derivative here. Remember on the absolute values, well, maybe we didn't actually do it quite like this, but remember on the absolute values what we did? We spread it into piecewise. I think that would be helpful here. Remember, you could have the minus of x minus 1 or just x minus 1, depending upon which x you're talking about. Here it's if x is less than 1, and this is if x is greater than or equal to when you place it. Yes, remember that? Remember splitting it off into piecewise? Yeah. And so that's helpful here because what's the derivative of this function? Well, it depends. If it's this piece, what's the derivative? Negative 1? If it's this piece, it's positive 1. So if x is less than 1, it's that. If x is greater than 1, and notice I left off the equal to part because it's this one has the corner. Remember this, the absolute value would have the corner at 1. So I left that off for a reason. But anyway, quick review of that. Nothing else that I'm sure you remember that. But anyway, back to our question here. The question was, is there a number C such that f prime of C equals this 1/3? Nope. The only derivatives f has is negative 1 and positive 1. So the answer to the question, is there a number C? No. No, there is not. So the question is, why doesn't that contradict the conclusion? Why doesn't this contradict the conclusion of the mean value theorem? Well, it's back to hypothesis, isn't it? If one of those hypotheses isn't satisfied, the conclusion is not valid. Which of the two hypotheses is not satisfied here for this function on 0, 3? Is it continuous on 0, 3? So is the function f of x equals absolute value of x minus 1 for hypothesis 1 continuous on 0, 3? Well, again, review here. This graph looks like this. Graph it. You need to, but it's the V shape. It's continuous everywhere, isn't it? There's no breaks, there's no discontinuities, okay? So yes, it is continuous on 0, 3. However, hypothesis 2, what do you got? F of x equals x minus 1. Differentiable on 0, 3? well, I gave it away just a second ago. Nope, why not? You got a corner. Right. Nope, it's not differentiable at x equals 1. So that's why it doesn't contradict. Why doesn't this contradict the conclusion? Is because the second hypothesis isn't satisfied, and so your conclusion, you won't have that conclusion as a valid conclusion for that particular function on that particular interval. Now, if we had chosen, off the interval that did contain 1, we'd be okay, because everywhere else it's differentiable and continuous, except at 1. So as long as you didn't pick 0 to 3, the interval that had 1 in it, you'd be okay. All right? So, yeah, so why doesn't this contradict? You just say, well, hypothesis 2 isn't satisfying, okay? So all bets are off on the conclusion there. Any questions? That look okay?